Hello there and welcome to Pluralsight. This is Tim Warner and the name of this module is TCP-IP Basics. Let me quickly introduce you, or reintroduce you as the case may be, to the Pluralsight learning path for the CompTIA A+ 220-901 certification. A learning path consists of a series of courses, the first of which is a general introduction, and then the other courses, hardware, which we just came out of, networking, what we're doing now, mobile devices, and finally troubleshooting, all correspond to the CompTIA published exam objectives. We are at Pluralsight a CompTIA partner, so you can rest assured that I'm giving you full spectrum 100% coverage of every objective. In this networking course, let me quickly show you the lay of the land module-wise. We began with network cables and connectors and are now delving into the transmission control protocol, internet protocol suite. As a matter of fact, this is the first module of a mini-series that will finish in the third module, ports and protocols. Then we turn our attention specifically to the wireless arena. Then we get into small office, home office networking, internet connection types, network architecture devices, and ultimately networking tools. What are our learning goals for this module? First, we're going to start by giving you the lay of the land with TCP/IP. As an instructor, I always have to be careful in terms of what I assume of your knowledge coming in. We'll cover the OSI reference model and MAC addresses there. Then we'll spend some time on how IP addresses work, how they're constructed, how they're divided into two version spaces, IPv4 and IPv6. Then we'll break out our demo and I'll give you some really valuable skills on configuring TCP/IP on client devices. We're going to cover Windows, Linux, and OS X there. And by the end of this module, you'll also understand network services and internetworking devices a bit. I'm talking about things like the switch and the router. Let's get started. Meanwhile, in the real world, as a working computer repair technician, you may be asked, in fact, this is probably one of the most common complaints you'll see, regardless of the environment of your workplace, is I can't connect to the internet. Remember that many of your customers don't have a grasp of technical terminology, so you're going to have to just take what they tell you and run from there. Another question, and this would be more from an IT perspective, you may be asked for your advice, hey, do I need to worry about Internet Protocol version 6, or are we cool just doing IPv4? We'll revisit these questions, of course, at the end of the module. We're covering a single exam objective here in this module, specifically 2.3, which states that we need to be able to explain the properties and characteristics of TCP/IP. TCP/IP Basics. The Open Systems Interconnection Reference Model, or OSI as it's normally called, is a model that standardizes host-to-host communications. Now, there have been several networking protocols over the last several dozen years, but Ethernet has been the predominant one, and it's the only one that we really need to worry about nowadays. And as far as the protocols, which are the rules that computers follow when they transmit data, the protocol suite of choice now in business and even in residential interconnectivity is TCP/IP. A host is nothing more than a device that has a network interface card and can receive and have an IP address and communicate in a TCP/IP network. Now, the International Organization for Standardization developed this OSI reference model as a way to do a vendor-neutral schema for defining host data communications. It's actually codified in an ISO IEC standard. Check the course notes because I give you the appropriate links if you're the kind of nerd who likes to read up on this stuff. Understand that the OSI reference model is a 7-layer model. We'll cover the 7 layers in just a moment. That makes it easier, among other things. It helps us as working professionals to do troubleshooting, but OSI also makes it easier for vendors. Think of manufacturers like Netgear and Cisco and IBM who make network interface cards and network appliances. These vendors can develop products knowing that as long as they write their drivers and their applications to work with standard TCP/IP protocols and port numbers, and according to the Ethernet standard overall, that will have interoperability seamlessly between, say, an Apple iMac running TCP/IP and a Microsoft Windows server, and let's just throw in a CentOS Linux machine to boot. They'll all be able to communicate with each other. And that's what you see at right, this layer of hardware and software. At the lowest level, the hardware would be the network interface card, and then we have the operating system and the device driver that functions to associate that network interface hardware with ultimately applications like, say, a web browser or an email client that uses the TCP/IP model. A mnemonic device is an easy way to memorize information. There are 7 layers to the OSI model, and the 2 mnemonics that I've used. You should know the OSI, just the very basics, before you take your 901 exam. I know, as I've said in the previous module, that we're overlapping here with coverage from the CompTIA Network Plus, but you do have to have these basics down. There's all people seem to need data processing. That takes you from OSI layer 7 down to layer 1, or the other way, to start at layer 1 and move up. The one that I use, especially because I love pizza, is please do not throw sausage pizza away. Now you're probably thinking, Tim, why are you giving us these mnemonics? You haven't even given us the OSI model yet. Hang on to your hats, that's what we're doing right now. Don't be overwhelmed. This is a pretty intense slide. I crafted this diagram in Microsoft Visio, and it shows you just in one shot the OSI reference model. Now let's just look at the left-hand side, because you'll notice that I've duplicated the model because I'm intending to show communication between 2 TCP/IP hosts. For instance, on the left side, I guess that's gray, the blocks are. Let's imagine that that is a computer that's going to be where the user, I should say, is opening a web browser and is going to load a web page from a web server, and the right side, I guess those blocks are green, would represent the web server. Now you'll notice that those OSI layers are numbered, as I said, 1 through 7, and you'll notice also that I have horizontal arrows connecting the 2 hosts, because as it happens in network communication, you have host-to-host communication across layers. Now what do I mean by that? Well, let's take it from the top. On the left side, let's imagine that this user is opening a web browser. They type http://pluralsight.com and they press enter. The application will take that request and begin to break it down into smaller segments. So 7 deals with the end user application. 5 and 6 deal with taking that data down to its initial raw form. It could be Unicode or ASCII text. There could be compression going on, encryption, decryption. At OSI layer 5, the session layer, that's responsible for opening, maintaining, and closing a communication session. So again, you notice that we have that logical connection between the web client and the web server on the other side. At layer 4, the data is called a segment. That's what you see at the left. Those acronyms and so forth refer to the protocol data units, or PDUs, how network professionals refer to data at each layer of the OSI. At OSI 4, at the transport layer, that's a very important layer, because the computer and the TCP/IP stack needs to determine, do we need reliable delivery, which means TCP protocol, or do we just need low overhead best effort delivery, which is the UDP protocol. By the way, we're going to be revisiting TCP, UDP, and these OSI layers repeatedly throughout the rest of this course. At the layer 3 level, this is where the router comes in, and this is where IP addresses come into play. At OSI layer 2, the data link layer, this is where the switch operates, and this is where the media access control, or MAC hardware addresses come in. And then finally, before the data goes out onto the medium, either Wi-Fi or wired Ethernet, the data is broken down into bits, 0s and 1s, and that's handled by the network interface card and its device driver. As far as takeaways at this point, I want you to memorize OSI 1 through 7, just their names, and I want you to remember that the router operates at layer 3, the switch operates at layer 2, and the network interface card operates at layer 1. Now, OSI model is a conceptual model, but I need you to understand that you actually use it as a working IT professional. This is a living standard. I've been in the industry since 1998 or so, and I can tell you I've used the OSI in the real world. For instance, I might be troubleshooting a user who claims they can't connect to the internet or even any LAN resources, and if I go to the switch and see that there's not a link light on the port, I can look and say, that's probably going to be a layer 2 problem. In other words, there's probably something messing up the TCP/IP stack on the client's computer, or maybe there's an issue on the switch. If I find out that the user unplugged their computer, that's a common solution, unplug it back in, that would be a layer 1 problem. If it's a problem with routing, where a user can't connect to resources on another network segment, that would be layer 3. You see what I mean? So the OSI is truly a very useful model. model. Now, we use different tools to visualize that layer data. It's one thing at the physical layer because you can see and touch network cables and ports and so forth, but then you need to turn to tools. Like in the lower left of the slide, this is a toner and probe kit where you can test continuity on network cables and so forth. And then there are software tools like Wireshark is my go-to protocol analyzer of choice. As a matter of fact, my colleague and friend Ross Bergertis here at Pluralsight did some really good Wireshark training, so consider looking at that in the library. Now, I mentioned that MAC addresses, or Media Access Control addresses, operate at OSI Layer 2. What is this? What is a MAC address? I'm not talking about the McDonald's Big Mac for sure. What I'm talking about is a hardware address, or a burned-in address that is encoded permanently in the firmware on every network interface card. And remember that a TCP/IP host isn't necessarily just a full-size computer or a laptop. It can be your smartphone, your cable modem at home. Any device that's network capable and has a network interface card is going to have a MAC address associated with that card. It's a globally unique identifier, and it's meant to be a permanent address that doesn't change. An IP address, on the other hand, is a logical address and can very easily change. For instance, my iPhone has one IP address when I'm at work in my office and I'm connected to my router, my Wi-Fi router, or if I'm out and about using my AT&T LTE service, I'm going to pick up another IP address. They're subject to change at any time. Now, it is true that you can easily spoof or change a MAC address, but officially, each network interface has one and only one permanent address that you can find perhaps literally on the device on a sticker. You might actually find the MAC address printed on the card permanently, and you can certainly retrieve MAC addresses through software. I'll show you that in our demo. The numbering system for MAC addresses is different from what we use in terms of base 10 decimal. We use a larger number system, hexadecimal or base 16, because MAC addresses are a lot longer than most decimal numbers that we deal with. The base 16 means that the first 10 places go from 0 to 9, and then places from 11 to 16 are represented as A, B, C, D, E, F. Here's an example of a MAC address. A MAC address is 48 bits long. You might need to memorize that for your exam. You do want to walk into the exam having a mental catalog of some of these statistics. And 48 bits means 48 binary digits, zeros or ones. Because a whole string of 48 zeros and ones is a huge, ginormous number that nobody wants to write down, MAC addresses use the hexadecimal notation system, and you'll notice that you get a string of hex digits. You get 1, 2, 3, 4, 5, 6 groups of hex numbers, with each section representing 8 bits. As a matter of fact, each hex digit is represented in binary with 4 places. If that's a little confusing to you, you can check the Pluralsight library. I give you in the course notes some heads up on that. But all you need to know for the A+ is that MAC addresses are represented in hexadecimal. They're 48-bit addresses. And the first half, which is the first 3 groupings of 2 hex digits, is going to be specific to the vendor of that network interface card. The IEEE is the worldwide holder of the MAC address space, and vendors, if let's say we decide to go into business to build network interface cards for smartphones, we will apply to the IEEE for an organizationally unique identifier, a prefix that we'll add to all of our MAC addresses. The benefit of the OUI is that it prevents a collision from taking place, such that an Intel NIC won't conflict with a Netgear NIC because the OUIs are different. The OUI standardization also makes it easier from a network management point of view because you can target network policy based on that OUI to hit only specific make and model network cards that you know are associated with particular hosts. So the last 24 bits are vendor assigned. Ultimately, every TCP/IP host will have a globally unique MAC address. IP addressing. You know, TCP/IP does not refer to a single protocol. It doesn't even refer to 2 protocols, although TCP stands for the OSI Layer 4 Transmission Control Protocol, and IP stands for the Layer 3 Internet Protocol. TCP/IP is actually a protocol suite or a protocol family that has a couple dozen or more protocols that all can function together. The Internet Protocol is probably the one that you'll use most in practice and troubleshooting and so on. IP version 4 has been around since 1981, defined in a document called a Request for Comments, RFC. RFCs are where all of your networking standards and your web standards are codified. A nonprofit consortium called the Internet Assigned Numbers Authority, IANA, maintains the IPv4 address space. Now, because IP addresses are only 32 bits long, that gives you only 4 billion or so unique possibilities. Back when IPv4 was young, that was fine. In fact, when I got into IT, it was common for a business to be given a pretty large block of public, globally routable IP4 addresses, and you just went from there. But nowadays, I mean, each person probably consumes several IP addresses at a time, so it would make sense, and it's true, that for all intents and purposes, the public IPv4 address space has been exhausted. Like I said, an IPv4 address is a string of 32 zeros and ones. And if you do the math there, the permutations, that turns out to be only about 4.2 billion, which seemed like a lot 20 years ago, but is not today. Now, an IP address always functions in concert with what's called a subnet mask. And that subnet mask is what allows a TCP/IP host to determine what network segment it's on vis-a-vis what network segment another machine that it's communicating with is on. And that comes into play very importantly every day. Specifically, if the host determines that the computer it's wanting to connect to is on a different network segment, the local host is going to need a default gateway address, which is a router interface that can get those packets out of the local network segment and reach the destination. IPv4 addresses, like I said, consist of 32 zeros and ones. Now, whereas we saw with the 48-bit MAC address that we use hexadecimal notation to make it more compact and easier to work with, what we do with IPv4 addresses is break those 32 bits into 4 8-bit sections, and then you convert from binary to decimal. Now, all the conversion math isn't relevant for us right now. Just know that that turns out to be, as you see, 4 sections called octets that range decimally from 0 to 255. And as I said earlier, the subnet mask functions to block off some of the IP address, and that block off is the boundary line between the network identifier of that host that's shared with other hosts on its network segment and its unique host identifier, which you see at right. IPv4 addresses are broken into classes, A, B, C, D. There's some others that we don't need to worry about. The classes are easily identifiable by looking at that first decimal number, the first octet in the address. If it's between 1 and 126, that's, at least originally, a Class A address and uses the Classful mask 255000. By the way, 8 ones, 8 binary ones, translates to decimal 255. So you can think of the mask very much like a real mask would. If you took a mask like a bandana and covered half your face, that's how I envision when you overlay a mask on an IP address. You're serving to mask or separate two parts of the address. Once again, that's a separation between the network and the host portion of the address. Now, classful means that those classes are divided at octet boundaries. So a Class B address uses a 255.255.00 mask, and the first octet goes from 128 to 191. Class C, that's a 24-bit network. The mask is 255.255.255, and the first octet is 192 to 223. And Class D addresses have a first octet value of 224 to 255, and those are used in IP multicasting. Multicasting is a way to save network bandwidth by, instead of sending data from host to host, you can send data to a single target address and have multiple targets sharing that same receiving address. That can be useful during video or teleconferences where bandwidth may be at a premium. The loopback address is a reserved IPv4 address. There's actually IPv4 and IPv6 loopbacks. You need to know that the IPv4 loopback is 127.0.0.1, and this is used for diagnostics. It's a good idea when you're testing connectivity to do a ping on 127.0.0.1. If you get replies, then at least you can have a sanity check that the TCP/IP protocol stack works on that machine. Now, whereas classful addressing is divided into A, B, C, D, etc., and the networks are divided at bit boundaries, first octet, second octet, third octet. you can actually do CIDR, or classless interdomain routing, or classless addressing, to do a network break at any bit boundary. This is useful when you create subnets, when you're starting with a large pool of addresses and you want to subdivide it into separate, smaller networks to partition out your network for performance and security reasons. Now, when you do classless addressing, you give the network address, which in this example, 192.168.0.0/19, that tells us that we're starting with what looks like a default class B shape, where the first 16 bits are the network ID, and the zeros just refer generically to the network itself. But instead of doing a /16, or 255.255 mask, if we do a /19, which means that we're using the first 19 bits of that address to do networks, then that's going to change the subnet mask that we're going to use to 255.255.244. And if you do the math, I should say, that will give you, instead of just one great big pool of addresses, you'll get 8 separate subnetworks, each supporting up to 8,190 hosts per subnet. Again, the reason why you might want to do this, called subnetting, is for performance reasons and for organization reasons and security reasons. Now, I told you that the 32-bit public IP address space has been exhausted, so what do? For instance, at home, if you do an IP config or an IF config to look at your home computer's IP address, chances are it's an address that starts with 192.168. In Request for Comments 1918, we have defined ranges of reserved private addresses that cannot be routed. Routers will not pass these packets out onto the internet. So whenever you see an address that starts with 10, or an address that starts with 172.16 or up to 172.31, or finally an address that starts with 192.168, we're talking about private non-routable addresses. So yes, that does bring in overhead, because when you think about it, your home cable modem router is going to have one and only one publicly routable IP that you're being leased by your internet service provider, but then you might have 15 hosts inside your home between your game console and your smartphone and your computers. So there has to be some kind of network address translation between the private address and the public address, and that's actually the case, but we don't need to talk about that now. Now, link local addresses, or as Microsoft calls them, a PIPA, automatic private IP addresses, is yet another reserved range that is used as a way such that if a computer cannot get an IP address from, say, a dynamic host configuration protocol, DHCP server, the network interface will auto-assign address in the range of 169.254 with a 16-bit subnet mask. You might have noticed that in the past. If you can't connect to the internet, you do an IP config and you're thinking, well, how in the world did I get this 169.254 address? That's an auto-assigned address, and what's neat about that is that, number one, it at least keeps your TCP/IP stack alive, but number two, it also allows that host to communicate with other hosts on the same network segment, because once again, we're using the same network address portion for all the hosts on that segment. So Internet Protocol v4 is long in the tooth for sure. So we now have, and have had for the last several years, although you wouldn't really know it, a next generation IP stack, the IP version 6, that was finalized in Request for Comments 1883 and 1996. Check the course notes because I give you all the RFC links. They're freely downloadable, you don't have to pay for them, and they're also written in non-technical language. IPv6 is meant to solve the address depletion of IPv4 because IPv6 addresses are a whopping 128 bits long. That's 5 times 10 to the 28th. That's 5 with 28 zeros after it, addresses for every person on Earth. So again, with technology, you think today, oh, we'll never reach that limit. You know we will, but hopefully it's going to take us a long time. Some other things that have been corrected in IPv6 that were problematic or are problematic in IPv4 are that the header structure in IPv6 is a lot simpler. There's no broadcast with IPv6. v4 tends to be pretty chatty and tends to put a lot of network pressure on a network. You don't get that with IPv6. There's also built-in encryption, and most importantly, IPv6 is built to coexist with IPv4. I'll bet you use IPv6 every day and you don't even know it. The address format for IPv6 is pretty intimidating, I have to be honest. Again, we turn to hexadecimal because these 128-bit addresses are absolutely huge. By default, the 128-bit hexadecimal address is broken in two, with the first 64 bits denoting the network and the second 64 bits for a node. Now notice that that 64-bit node section is twice as long as binary. It's actually much more than twice the number if you do the math. But in terms of bit length, it's doubling the bit length of IPv4. Specifically, an IPv6 address consists of 8 groups of 4 hex digits, with each group representing 16 bits, or 2 octets in IPv4 language. You can drop leading zeros. You can do a couple different things on making IPv6's addresses a little easier to manage. And DHCP is a network service called Dynamic Host Configuration Protocol that's meant to simplify the distribution of IP addresses. So you think with IPv6, these honkin' long addresses, any help you can get to accurately deploy IPv6 addresses is going to help, and that's definitely true. Here's some examples. The quad A refers to how IPv6 addresses are represented in the domain name system, or DNS. We'll talk about DNS at another time. But you see it right. We have an IPv6 address. This is a public address, globally routable, and you're thinking, my word, how can I write this down? If somebody says, what's your IP address? Am I supposed to remember this? There are some tricks. You can compress all of the contiguous zeros and represent that as double colon. You also can strip away leading zeros, which leads to a little bit more compact. But yeah, no doubt about it, IPv6 addresses are pretty gnarly looking. Moreover, with IPv6 addresses, another thing that helps not having to know those long numbers is SLAC, or Stateless Address Auto Configuration. By default, any IPv6 capable system is going to auto-generate a link local address that starts with FE80. Know that for your exam. So an FE80 address is going to allow hosts, in the example at left, on one network segment, they can communicate with each other just fine. But these link local addresses are not going to pass through a router, and so therefore a host from the top network segment is not going to be able to communicate with one on the bottom, and vice versa, using just those link local addresses. The loopback diagnostic address in IPv6 is ::1. Again, know that for your A+, just in case CompTIA asks you. Client IP configuration. What do we need to do from the client standpoint to get a user on the network, the local area network and beyond? Well, first thing, as a network administrator, you need to determine which hosts need statically reserved IP addresses and which ones can do DHCP dynamic addressing. Easy way to split, well, I'm not going to say easy because I don't want to trivialize it, but in general, your users and the user base population should all be DHCP clients who automatically get their IP from DHCP server. Servers specifically should definitely have static IPs because you don't want those IP addresses subject to change. The nature of dynamic addressing is that a client can go offline, the user can shut down the computer, turn it back on, and they might get their old IP address back from DHCP, or they might receive a new lease if their old address has already been given to someone else. Now, I shouldn't say given. DHCP operates on a lease basis, not a gift basis. Network printers would be another candidate for static addresses. Wireless access points. Any server-side services should be static in general. A subnet mask is going to be shared by all hosts in that TCP/IP network, and a default gateway refers to a router address that's on your own network segment and serves as a way to get out of your network segment if you have to go to maybe another part of your business's network, or potentially out your internet router to the world beyond. I mentioned domain name system briefly a couple minutes ago. DNS is another way that makes TCP/IP communication easier because you can just use computer-friendly names, host names, instead of having to know an IPv4 or, heaven forbid, an IPv6 address. IP internetworking. This is an important drawing that kind of summarizes most of what we've learned thus far. Don't be freaked out by all the IP addresses. We'll take it just a piece at a time. Notice that this network is divided into two segments. When I use the word network segment, another term for that is subnet or subnetwork. Another term yet is a broadcast domain. Now you see in the upper left, the host has 192.168.1.232 with a 24-bit subnet mask. So in other words, the network ID on this left network is 192 192.168.1.0, okay? Now, on the other side of the network, where we have a couple servers, notice that the network ID there is 192.168.2.0. How can these hosts on each of these network subnets communicate with each other? You'll notice that they're locally plugged into a switch. A switch is a layer 2 device that serves, among other reasons, to get your hosts connected to your network backbone. They can do other things, but one thing that most switches, at least pure layer 2 switches, can't do is route traffic from one subnet to another. So you'll notice that each switch is also in turn plugged in to a router interface. That router has a separate interface that's connected to each subnet, and each host on each subnet in its IP configuration is pointing to its local router interface as its default gateway. So the .232 and the .66 machines have 192.168.1.1 as their default gateway, and our .15 and .16 hosts are using 2.1. All right? So the great benefit there is if 232 wants to communicate with .66, the local host is going to take its 24-bit mask and compare the network ID from one to the other. Of course, .232 will see, oh, 66 is on my network, so I'll directly communicate with it. If 232 needs to communicate with .15, again, we're going to use the subnet mask to compare network IDs, and 232 will resolve, well, .2 is not on my network. I'm going to send those packets to my default gateway and let the router figure out how to get there. Speaking of switches and routers, I wanted to show you some real hardware just briefly because we've been looking at a lot of Visio and logical diagrams. These are Cisco Catalyst switches, and at left we have, do you see what kind of port shape that is? Those are RJ45 jacks, aren't they? And then on the right we have what are called SFP ports, which are one-size-fits-all ports. You can put fiber in there, you can put all sorts of different interfaces. And you'll normally do something like a fiber interface to do a high-speed uplink to your router or to another switch. Switches operate on the basis of the layer 2 MAC address, and they know the MAC address of every host that's plugged into each of its ports. This is a Cisco 3600 series router. You'll notice that the router has far fewer interfaces than a switch does. What's neat about routers is that in addition to segmenting a network with physical interfaces like the two you see here, you can actually create sub-interfaces to give the router more routability, for lack of a better term. In this brief demo, I'm going to show you how to do client-side TCP/IP configuration in 3 common client operating systems. This is Windows 8.1, and I'm going to right-click the Start Screen button. This is a shortcut way to get to this really neat little flyout. I'm going to go to Run, and in the Run box, I'm going to type ncpa.cpl. That's a really good shortcut for you to know because it takes you directly to your Network Connections folder. I'm going to right-click this guy and go to Properties. Notice that this is something that you have to be an administrator on that machine to do. And notice that we have entries for both TCP/IP v4 and v6. I'm going to double left-click v4, and you'll notice that I'm set as a DHCP client. So I'm going to obtain my IP information from a DHCP server. Now let me open up a PowerShell console, and I'm going to type ipconfig. Notice that this machine does have a Class C style IP address. My default gateway is 7.1. And notice that my network card has given a link local FE80 address as well. Now, let me CLS to clear the screen. ipconfig all is what you want to use if you want all information. And in particular, I want to draw your attention to the physical address, which shows the MAC address. And I also want you to see we have DHCP information here. Our DHCP server is also 7100. And we have details about the lease, when we obtained this lease and when we're going to lose it. Now we'll go to Ubuntu Desktop Linux. There's a few different ways to get to your network settings. In Ubuntu, there's this little widget up here, and you can come down to Edit Connections, and you'll see that I have 2 network interfaces, one called internal and one called external. I'll select mine and say Edit. Again, it gives us the MAC address, the hardware address. Linux historically gives you a lot more control over your settings, so notice that you can actually spoof a MAC address very, very easily there. If we go to IPv4 settings, you'll see that this is an example of a manually assigned IP address where I plugged in using add here 6.9 with a 24-bit mask and the appropriate gateway address. And let's close out of here and bring up a terminal. As far as diagnostics go, ping, If you get responses on localhost or 127.0.0.1, that's a good thing. If you know the IP address of your target, like my local router interface, which I believe is 6.1, you'd want to try that next. You want to get responses. Let me clear the screen. And I'm actually plugged into a DNS server here, so I can specify a host name, and now I can successfully ping a host that's on a remote subnet. So I'm going through my router here to connect to my DC1, which is a Windows machine. And finally, here we are on Apple's OS X operating system. There are various ways to get to our network preferences. I'm going to open the Apple menu and come down to System Preferences, and then into the network item. I'm going to focus on my wired Ethernet connection here, and we can just see here very quickly that I am using DHCP, although you can override that if you want to, and verify our IP address, our subnet mask, our default gateway, our DNS. It's not giving us the MAC address though, is it? So let's go to Advanced and see maybe on the hardware page. Sure enough, there it is right here. Cool. So the take-home message I have for you here and showing you the client-side settings is that it's the same standard vocabulary. Once you understand IP addresses and subnet masks and default gateways and so on, and DHCP of course, then you should be able to confidently troubleshoot regardless of what operating system you're dealing with. Let's return to the real world and address those two questions. The first of which is one that you're going to have nightmares about in your career. I can't connect to the internet, and the other one was about IPv6. In terms of the I can't connect to the internet, think of the bottom OSI layers. Think layer 1 is the user's computer, their network interface plugged in. If it's a Wi-Fi connection, is their Wi-Fi radio turned on? Layer 2, do they have a link to the switch? Is there a green light illuminated on their own computer by their RJ45 port? And is there a green go light on the switch? And you can just work your way up from there. With IPv6, as an IT pro, I would say yes. I don't know if you need to worry about IPv6, but you need to be aware of IPv6, and I would strongly suggest you learn it now. For homework, I have two assignments for you. One, I want you to use DIA, which we learned about in the previous module, to create a physical device IP map diagram of your home network. I want to see all of your hosts and their associated details, their MAC addresses and their current IP addresses and so forth. I'd also challenge you to figure out how you can show IP address, subnet mask, MAC addresses on non-standard hosts, maybe your smartphone, if you have a game console like an Xbox or a PS4, your digital cable DVR box. Because those are all TCP/IP hosts, you should be able to view those details. For further learning, draw your attention to Ross's course for the Cisco CCNA certification, Introduction to Networking. See his module called the OSI Model and Encapsulation. That will give you very well-stated, well-taught fundamentals on the OSI. Ed Horley, a guy I really admire a lot, did a course on IPv6 called Introduction to the Protocol. It's 2 hours, 30 minutes, well worth your time. Please watch that. In summary, IPv4 is not going anywhere soon, but please be proactive about IPv6. That's my parting advice to you. Second, as I've said at the end of the demo, once you understand the basics of TCP/IP, you can confidently perform configuration and troubleshooting regardless of the OS. In our next module, we're going to drill in even closer in TCP/IP and pay particular attention to ports and protocols. Thanks a lot for your participation. I'll see you then.